It is nearly the same size as Earth. It formed from the same swirling disk of gas and dust. It orbits the same star. From a distance, it looks like a twin, another rocky world born from the same cosmic blueprint. If planetary formation follows consistent laws, then Venus should spin the way Earth does, in the same direction as its orbit, aligned with the rest of the solar system. But it doesn't. Venus rotates backwards. While most planets spin counterclockwise when viewed from above the Sun's north pole, Venus turns clockwise. The Sun rises in the west and sets in the east. A day on Venus lasts longer than its year. It takes about 243 Earth days to complete one rotation, yet only 225 Earth days to orbit the Sun. It is slow, inverted, and deeply strange. At first glance, that sounds like an astronomical curiosity, an odd detail to memorize and move on from. But the more you look at it, the more unsettling it becomes. Planetary rotation is not random. It is inherited from the angular momentum of the protoplanetary disk, the vast rotating cloud that birthed the Sun and its planets. When that cloud collapsed, it spun, and that spin should have imprinted itself onto the worlds that formed within it. Most of them obey. Mercury spins in the expected direction. Earth does, Mars does, Jupiter, Saturn, Uranus, Neptune, all rotate roughly in line with the solar system's original motion. The pattern is so consistent that it feels like a rule. And then there is Venus. It doesn't just spin the wrong way. It spins extraordinarily slowly. If you stood on its surface, ignoring the crushing pressure and searing heat, the Sun would crawl backward across the sky. The world would feel paused, as though time itself were reluctant to move. The contrast is sharp. We assume the universe follows clean, predictable mechanics. We build models of formation, equations of motion, simulations of early chaos that settle into order. And in many cases, those models work beautifully. They explain orbital resonances, planetary tilts, asteroid belts. But Venus refuses to fit neatly. This is not a minor deviation. It is a planet-sized contradiction. If the same physical laws governed Earth and Venus, why did one inherit the expected spin, while the other reversed itself? What event was powerful enough to rewrite its motion? And why does no explanation feel entirely complete? The deeper question is not about Venus alone. It is about how confident we are in our cosmic narratives. When a planet defies the pattern, it forces us to confront an uncomfortable possibility. Maybe our models are correct but incomplete. Maybe formation is not as tidy as we imagine. Maybe the early solar system was more chaotic, more violent, more sensitive to subtle forces than our simplified stories suggest. Venus is often called Earth's twin, but in its backward rotation it behaves less like a sibling and more like a warning. To understand why Venus is such a problem, we first need to understand what should have happened. The solar system did not form in pieces. It began as a single enormous cloud of gas and dust drifting through space. Under the pull of gravity, that cloud collapsed inward. As it contracted, it began to spin faster, just as a figure skater spins faster when pulling in their arms. This is the conservation of angular momentum, a principle so reliable that it governs everything from spinning tops to orbiting galaxies. Once that cloud flattened into a rotating disk, the Sun formed at the center. The remaining material continued orbiting in the same direction, colliding, clumping, and gradually building the planets. Each planet inherited a portion of the disk's original spin. The result should be predictable. Planets orbiting the Sun in the same direction, and rotating on their axes in roughly that direction as well. And that is almost exactly what we observe. Earth spins counterclockwise. Mars does too. Jupiter, Saturn, Neptune, each follows the same general rotational pattern. Even Uranus, which appears dramatically tilted, still rotates in the inherited direction, just tips sideways. The expectation is clear. When a rotating system fragments into smaller bodies, those bodies retain the parent's motion. It would actually require something dramatic to reverse that direction. This is where the contrast sharpens. Venus does not merely tilt. It does not merely wobble. It spins backward. Its axial tilt is about 177 degrees, meaning it is nearly upside down compared to Earth. Instead of modest variation within the inherited pattern, Venus appears to have abandoned it entirely. Physics does not casually permit that kind of deviation. In the early stages of planetary formation, countless small collisions would have nudged and adjusted a planet's rotation. Minor impacts could alter speed, slightly shift tilt, introduce irregularities. But reversing spin entirely would demand either an enormous disturbance or a prolonged external torque powerful enough to overcome the planet's original angular momentum. That is not impossible, but it is not trivial. The original protoplanetary disk was massive and coherent. Its rotational imprint should have been strong. For Venus to end up rotating retrograde, something must have significantly rewritten that inherited motion. And yet, when we model solar system formation, most simulations naturally produce prograde rotation. The mathematics prefers alignment. Disorder can emerge, but wholesale reversal requires specific conditions. This is why Venus unsettles planetary science. Because according to the standard narrative, planets formed from rotating disks inherit their spin and maintain it, unless acted upon by extreme forces. The laws are consistent, the principles are clean, angular momentum is conserved, and then quietly Venus turns the wrong way. The universe usually rewards simplicity. Here it presents complication. The most common explanation for Venus's backward rotation is dramatic and intuitive. Something hit it. In the early solar system, collisions were not rare events. They were the rule. Growing planets slammed into one another in chaotic, violent encounters. Earth itself likely experienced a massive impact that formed the moon, so the idea that a giant body struck Venus and flipped its rotation seems reasonable. If a sufficiently large object collided at the right angle, it could in principle reverse the planet's spin. Angular momentum can be transferred. A strong enough blow could overpower the original prograde rotation inherited from the protoplanetary disk. On the surface, the theory feels satisfying. It preserves the broader model of planetary formation while assigning Venus's anomaly to a singular catastrophic event. But when examined closely, cracks appear. First, Venus does not just rotate backward. It rotates extremely slowly. Its day is longer than its year. A giant impact might reverse direction, but it would more likely leave the planet spinning rapidly in the opposite direction. Slowing a planet to such a crawl requires either extraordinary precision or additional mechanisms at work. Second, major collisions typically leave visible consequences. Earth's impact produced the moon and altered its tilt dramatically. Mars bears scars of enormous impacts across its surface. If Venus experienced a similarly titanic event, we might expect comparable evidence. Yet Venus's surface does not clearly display a single dominant basin that screams planetary scale flip. Its geology is complex, resurfaced by volcanism, but not obviously marked by one decisive collision that rewrote its rotational history. Third, simulations complicate the picture further. To reverse a planet's spin cleanly without shattering it or ejecting large amounts of debris requires specific impact angles and velocities. The window of possibility narrows quickly. It is not impossible, but it is not inevitable either. And then there is the question of stability. Even if a collision reversed Venus's rotation, would that configuration remain stable over billions of years? Or would solar tides and gravitational interactions gradually reshape it again? A single impact explanation begins to look incomplete when long-term dynamics are considered. The contrast becomes uncomfortable. The collision theory offers a clear narrative: chaos, impact, reversal. But planetary evolution rarely resolves so neatly. Venus's slow retrograde spin suggests not just a moment of violence, but an extended process of modification. So the leading explanation solves part of the puzzle while leaving deeper questions intact. It explains how direction might change. It struggles to explain why the final state looks the way it does. Venus may have been struck, but if it was, the impact alone does not tell the whole story. If a single catastrophic collision cannot fully explain Venus, then perhaps the answer lies not in one violent moment, but in slow, relentless forces acting over billions of years. Venus orbits closer to the Sun than Earth does. That proximity matters. The Sun's gravity does not merely pull Venus along its orbit, it also exerts tidal forces. Just as the Moon raises tides on Earth's oceans, the Sun can induce subtle distortions in Venus's shape. Over immense stretches of time, those distortions can generate torque, gradually altering rotation. Now introduce another unusual factor: Venus's atmosphere. Venus possesses an atmosphere far thicker than Earth's dense clouds of carbon dioxide wrapped around the planet under crushing pressure. This atmosphere does not sit passively, it circulates violently, generating powerful winds that race around the planet faster than the planet itself rotates. The upper atmosphere completes a full rotation in mere days, while the solid planet crawls beneath it. That imbalance creates frictional coupling between atmosphere and surface. Atmospheric tides driven by solar heating can apply torque to the planet's crust. Some models suggest that over hundreds of millions of years, this atmospheric drag could slow rotation dramatically and even contribute to reversing it. Unlike the collision theory, this mechanism does not require a singular dramatic event. It relies on persistence, small effects compounded over geological time, reshaping a world. But even here, certainty slips away. Simulations of solar tides and atmospheric torque produce possible retrograde outcomes, but only under specific initial conditions. The models depend on assumptions about Venus's early rotation speed, its interior structure, its atmospheric evolution. Change those assumptions slightly, and the results diverge. There is also the possibility of chaotic spin states. In complex gravitational systems, rotational axes can wander unpredictably. Subtle gravitational interactions with the Sun and other planets might have nudged Venus into a metastable configuration, neither fully stable nor entirely random, but delicately balanced. Chaos does not mean lawlessness. It means sensitivity. Tiny differences in initial conditions can lead to radically different outcomes over time. In such a system, Venus's backward spin may not be extraordinary. It may be the outcome of natural complexity amplified over billions of years. Yet this explanation too resists finality. Tidal models, atmospheric torque, chaotic evolution, each contributes part of the picture. None stands alone as definitive. Each introduces parameters that cannot be directly observed in Venus's deep past. The contrast becomes sharper still. Physics offers mechanisms. Equations can describe torque, angular momentum transfer, dissipative forces, but description is not the same as closure. Venus remains a case where plausible explanations accumulate without converging into certainty. Not because physics has failed, but because planetary history is layered, nonlinear, and sensitive to conditions long erased from direct observation. At this point, the temptation is strong. We have mechanisms, we have simulations, we have impact models, tidal torques, atmospheric drag, chaotic spin evolution. It would be easy to choose the most persuasive explanation, present it confidently, and move on. The anomaly would be absorbed into a tidy narrative. Venus would become solved. But that is precisely where the deeper lesson begins. Richard Feynman was famous not for claiming certainty, but for drawing sharp boundaries around what we truly know. He warned that the first principle of science is that you must not fool yourself, and you are the easiest person to fool. In planetary science, Venus is a reminder of that principle. We know the laws governing angular momentum, we understand tidal forces, we can model atmospheric dynamics. Those foundations are solid. What remains uncertain is not physics itself, but the specific historical path Venus took through those laws. And history leaves scars that time can erase. The surface of Venus has been reshaped by volcanism. Evidence of early impacts may have been buried or transformed. The initial rotation rate of Venus is not recorded in stone. The composition and evolution of its interior are only partially constrained. When we reconstruct its past, we are working backward from limited data, filling gaps with informed inference. That does not mean we know nothing. It means we know in layers. Some layers are firm, conservation of angular momentum, gravitational torque. Other layers are provisional, exact impact scenarios, precise atmospheric evolution. The danger arises when provisional layers are spoken with the confidence of fundamental laws. Venus rotates backward. That fact is secure. The explanation is still under construction. This distinction matters because science does not advance by pretending anomalies are resolved. It advances by keeping them visible, by resisting the comfort of oversimplification, by admitting where models fit imperfectly. Venus is not a failure of physics. It is a demonstration of how complex planetary systems can be. It is a case study in humility. The universe does not always conform to our cleanest expectations, even when the underlying laws remain intact. And perhaps that is Feynman's real warning. Mystery is not a weakness in science. Pretending the mystery is gone, that is.